Today we will discuss about some more intra-operation parallelism algorithms. So last session we were discussing about some operations like sorting, how we can do parallel sorting. We have seen two methods for doing sorting by using the mechanism intra-operation parallelism. Similarly, we have also seen the second operation, which is the join operation, where we discussed about 4 different algorithms that can be used for implementing the parallel execution of join operation. That is a single operation, intra operation, that can be executed in parallel. So we will see a few more similar algorithms or similar operations that can be executed in intra-operation manner. So the first one we are going to discuss is parallel selection. Parallel selection. So as you know, selection is the operation of selecting a set of tuples from the relation based on the given condition. So sometimes we will be selecting the entire tuples if you are not specifying any condition, or sometimes we will be selecting some tuples based on a given condition. So we will see how this selection operation can be executed in this intra-operation manner. So as you know, in relational algebra, this is the format of using select operation. That is, this is the symbol for select. Then under that we'll be having a theta that indicates the condition through which we'll be doing selection on tuples, and within brackets we'll be having the relation R. So select all the tuples from the relation R based on this condition. Select all the tuples from the relation R based on the condition theta. So that is the meaning of this selection operation. So here theta is so first selection that we are going to consider is the theta is actually using an equality or a comparison. That is, the condition is in the form of an attribute is equal to a given value. So in the first selection we are considering the equality condition for the selection of rows. So AI is an attribute present in the relation R, and that attribute value, if it is V, that is a given value V, based on that value we need to retrieve all the tuples with the attribute with this given value V. So where A is an attribute and V is a value, so that we have already seen. Now in this particular case, if we are using an equality condition for the selection of different tuples from the relation, here if the relation is, if it is partitioned on that attribute which is used for selection condition, now the selection process will be performed in a single processor. That means all the tuples with the attribute value that is given in the condition, that is AI is equal to V, that normally these tuples with this value will be residing in a single processor. So automatically the processor where we are having the value associated with the given attribute, and if the relation is partitioned based on the attribute which is used for providing the selection condition, so normally this selection will be performed in a single processor. But if the condition is in a different form, like if it is a range condition, for example, if we are going to retrieve all the tuples with of a student or of the employees with that is a salary between some range, salary between some 10,000 to 50,000. Okay, so sometimes like the condition will be in this range format. So here theta is considered for the selection of tuples based on a range condition. or it is between some range of values. Now in this particular case we are considering the relation is being partitioned in a range partition mechanism by using the attribute AI, which is used for providing this particular condition. So here this is only for specifying the range. Left hand side will be having a value, right hand side will be having a value, and this attribute value is residing between these two values. That is the specification given here. So it may be anything, salary between some initial value and some final value, or like salary less than, whatever be that range. It is not an exact equal value, it will be within a given range. So we will be producing some tuples, we will be producing more tuples which are coming under the given range. So this situation, it is not possible to use a single processor. That situation we need to perform the selection on different processes. So here the selection will be performed at each processor whose partition overlaps with the specified range of values. Okay, so we will see the situation. For example, if we want to retrieve all the tuples from the relation R with the condition that is the attribute with the attribute value E is equal to 3. Okay, so here it is an example pictorial representation of the first case, equality case. Now if this is the situation, we need to select all the tuples that is having the attribute E is equal to 3. What we will be doing is, if it is being range partition, now this is the condition. So here initially we were mentioning about, if the condition is an equality condition, we can directly execute the tasks based on a single processor. That is also possible. We don't know which type of partition that is being followed, but if we are using, especially when we are using some range condition, or even with this equality condition also, if the partition is done in a range partition format, we can easily refer to different number of processes. We can make utilization of different processes, and the different selection can be done on various processes, even if it is a equality condition on the set of the tuples present in a relation, or if it is a range condition, whatever it be. If the partition is done based on a range partition mechanism, we can utilize the different processes present in our computer system. So we can see in the below example that the condition given is the attribute E is equal to 3, and assume that the range partition, one range is here, that is the value, the attribute value is less than 10. All the tuples related to the condition with value of attribute E less than 10 is residing at one processor, which is given as R1, which is a partition. R1 is the partition of relation small r. Similarly, we are having another partition, that is R2, which consists of all the tuples which satisfies the condition, that is the attribute E which is having the value greater than or is equal to 10. All the tuples belongs to this condition will be residing at the second partition, which is called as R2. So here the condition given for selection is select E is equal to 3. That is the condition given. So automatically, so we'll be considering how it will be referring to a single processor. Okay, so if this is a situation, so this is the exact situation. Okay, so if E is equal to 3, one range is presenting in this particular partition, and second range is present in this particular partition. So automatically, if this is the condition, it will refer to only one partition which will be residing in a particular processor. Okay, so that is the procedure when we are using an equality condition. Now similarly, so this is the general condition, universal condition given for the entire set of tuples present in a relation. Now similarly, if it is being distributed, if the same thing, if the task is to be distributed among two different processes, we can apply the condition, that is the same condition, E is equal to 3 can be applied into two different processes. But automatically we can see that the value E is equal to 3 will be always present within this particular processor. Okay, now this is the modified version of the same diagram that is given here. The global condition which is given here, global condition, it is satisfying with the left hand side partition, it will be taking the tuples from this particular relation. But here also we are applying E is equal to 3, but we will not be getting the tuples with E is equal to 3 here, because it is having the values with different ranges. So automatically no need to refer to the second partition or the second processor which consists of this partition. Now assume that if the situation is a range partition, what will happen? If it is between two range, one range will be referring to this particular processor and the second range will be referring into this particular processor. Then it will select some tuples and it will select some tuples, and the entire tuples will be combined together to get the entire set of tuples that satisfies the condition, and all the tuples will be selected and that will be collected together into a single processor. So there are two situations. Normally if it is an equality condition that is applied for a selection, it actually requires to refer to a single processor only normally. That means that range of value that will be residing in a single processor only. The second processor need not be referred for accessing the tuples for that particular selection operation. But if it is a range, means if you are having some condition that consists of some ranges, we need to refer to different processes for selecting some tuples from one range and some other processor for selecting some other set of tuples that belongs to some other range. So this is the way how we are doing parallel selection. Now we will discuss about duplicate elimination and parallel projection. So we are not going to discuss in detail about all these algorithms. So what is this duplicate elimination? Duplicate elimination means while selecting the tuples from the relation, there will be some tuples which will be available in the relation multiple number of times. So normally we need to retrieve only once, those information to be retrieved only once. We don't need to repeat the same tuples again and again while expecting the result of a select operation. That is the selection by eliminating the duplicate tuples. So what we can do for this duplicate elimination? So while applying, so here for eliminating these duplicate tuples, we need to perform any of the sorting algorithm that we were discussing in our previous intra operation example by using sorting algorithms. So we will be applying sorting on the selected tuples, and while sorting itself, it will try to eliminate all the tuples which normally while sorting these tuples, the duplicate values will be gathered together. So that situation itself, so we need to apply it, we need to refer to a processor, we need to select the tuples. While doing selection, we need to apply a sorting algorithm on those tuples, and while sorting, the tuples with duplicate values will be gathered together, and from that we can eliminate all the other duplicate tuples by retaining only one tuples for our selection result. And it can also partition the tuples using either range partitioning or hash partitioning, and we can also perform the duplicate elimination locally at each processor. So see, this duplicate elimination can be done in two ways. After completing the entire selection on a single processor, we can apply a sort, and during sorting we can eliminate the tuples which are gathered together as a duplicate set of values. Second point is, if we are having more partitions available, we can do this duplicate elimination locally. Within each processor we can apply the same sorting algorithm, eliminate that. Similarly, the processor P1, P2, P3, for all the processor, it will select the tuples, eliminate the duplicates there itself, then finally the tuples without having duplicate values will be gathered together for performing or producing the result of that particular selection. So we can use any of these two methods, but for these two methods we require an additional sort operation for retrieving the additional tuples or duplicate tuples available within the relation. Now when we look into the projection operation, projection means what? Project normally represented by using pi symbol. Project the set of attributes like pi a1 comma a2 from the relation R. Just project on some attributes. We will not be selecting or projecting on all the attributes present in the relation. We need to project on only some selected attributes. Now projection without duplicate elimination can be performed as tuples are read in from the disk in parallel. So while reading the disk from different processes in parallel, while doing that reading the tuples parallel, that time itself we can perform the projection without duplicate elimination on the relation that is already available. So the relation may be available, the partitions may be available in different sites, different different processes. Now from each processor, when it is reading the tuples, for gathering, while reading itself we can eliminate, we can project on different attributes, and we can avoid other attributes present in the relation for selecting the tuples values based on the projected attributes only. Now if duplicate elimination is required, we can use any of the above given techniques. That is either by gathering all the tuples together and finally doing the sorting operation at a single processor, or else we can do the elimination on local processes and finally we can go for merging. So whatever be the mechanism, finally we need to extract only those required attributes for the production of result, because we will be projecting on only some selected attributes based on a given condition. So these are the procedures that are followed in duplicate elimination as well as parallel projection operation. Now we will be discussing about parallel grouping or aggregation. So in database, one of the commonly used operation is grouping, like sum of salary or count of employees, whatever it be. So we will be grouping a number of values together, a number of attribute values together, grouping the number of attribute values together. So here, while doing this parallel grouping or aggregation, we need to partition the relation on the grouping attributes. That is the main point to be considered. So if you want to perform this grouping, normally it is always better to partition the relation on the grouping attribute. For example, if you are going to perform sum of salary, now it is always better to partition the relation based on the attribute salary. So based on salary, So some salary tuples will be present in one processor, some other salary, some range salary tuples will be present in some other processor. So it is always better to have a partition based on the grouping attributes. Then go for computing the aggregate values locally at each processor. So that is the procedure that we are following for grouping. So one processor, one partition, do aggregate calculation there, then second processor do aggregate calculation there, third processor do aggregate calculation there, and finally we need to aggregate all the results that was gathered on local processor. So we can reduce the cost of transferring tuples during partitioning by partially computing aggregate values before partitioning. So we can reduce cost of transferring tuples. So if we are performing this aggregate operation in a single processor, we need to gather all the tuples present in all the processes. Means more data to be transferred. The cost of data transfer is more if we are performing this aggregate operations only in a single processor. That means all the range tuples from processor 1 need to be that is passed to that processor where we are going to do aggregation operation. Similarly, the second processor, all the tuples to be transferred. Similarly, from the third processor also, all the tuples to be transferred. But in order to reduce that, it is always better to do the aggregation locally and retrieve only those result of the aggregate operation, and only that data need to be transferred through the network for passing that to the final processor where we are going to find out the final aggregate value of that particular operation. So consider the sum operation. So here if you want to perform the summation of a number of values present under a particular attribute, what we are doing is we will be performing aggregation operation at each processor PI on those tuples stored on disk DI. So PA will be having the disk DI, and all the tuples present in that disk will be performing or finding the aggregation on that particular disk. Now the results in tuples with partial sums at each processor. So it will be each processor will be having the partial sums. Means whatever tuples are present in that particular processor, the summation will be found on that particular processor. Now the result of the local aggregation is partitioned on the grouping attributes, and the aggregation performed again at each processor PA to get the final result. So finally, after gathering all the local aggregate operation, result will be gathered together in another processor to get the final result. Now finally, if you are following this mechanism, we need to pass only some less number of tuples to other processes while performing this aggregation operation, where we need to apply this partitioning also. Now this is the pictorial representation here. So this is the processor P0 where we are having the entire relation present. So in order to do parallel operation, now we are considering initial partitioning of this relation into different processes. So some of the tuples will be moving towards D1, which is part of P1. Some tuples will be passed to D2, which is part of P2. Similarly, some tuples to D3, D4 and D5. So first of all, the relation, assume that the entire relation is present in a single disk, which is part of processor P0. So first of all, we need to do partitioning. So grouping partitioning. So based on if salary is the attribute that is used for grouping, it will be partitioned based on salary attribute. So some salary tuples will be moving towards D1, then some other salary to D2, similarly D3, D4 and D5 of each of the processor. Now after getting these tuples into the individual disk of individual processes, it will locally find out the summation. So for those tuples that are present in D1, the aggregate sum will be calculated locally within P1. Similarly, for those tuples which are present in D2, the summation will be calculated locally within P2. Similarly, for D3, for all the tuples present in D3, the summation will be applied in P3 locally. Similarly, for D4 also, it will do summation. Similarly, for D5 also. So, all the individual processor will be having the summation of those tuples which are present in its own local disk. Now, this is the partial computing of aggregation operation. Now after that, one of the processor, for example here P3, will be gathering the intermediate results into one particular processor. So here only the partial result are being transferred to the single processor P3, and it will apply one more summation on all the results that we are getting, and that will be stored in the disk that is associated with the processor P3 itself. Now the result is P0 with a relation, an entire relation within the disk 0 will be distributed or partitioned among different processes on different disk, and it will calculate the summation individually on individual processor. Then intermediate result will be consolidated on a single processor, and that processor will further perform the summation, and the result will be stored in its own local disk. Here we will be getting the result of the aggregate operation called as sum. For example, sum of salary of all the tuples present in all the processes will be gathered together. So what we are actually doing here, if it is being performed on a single processor, if the entire relation was here, and if we are applying this grouping within, so assume that we are having some 1 lakh tuples available. So applying this grouping on this 1 lakh tuples here itself will take more time on a single processor. But in order to avoid that, we are doing partitioning, distribute the tuples among different processes. Then some 50,000 tuples will be finding the sum here. Similarly, some other 50,000 here, 50,000 here, like that. It will be distributing the tuples and find the sum locally, and again consolidate the result alone into a single processor, and will be finding the result on a particular processor. So we are actually getting a speed up on the execution of the entire grouping operation. So single processor, a large relation, finding the grouping or aggregation will take more time when we compare that with the situation where we are having multiple number of processes available, and the aggregation is distributed among those different processes. I hope it is clear on parallel grouping or aggregation. Now we will look into the cost of parallel evaluation of operations when we are using this intra-operation parallelism concept. Now if there is no skew, so I was mentioning what is skew. Skew is actually the variation of partition. So some processor will be having less number of tuples, and some other processor will be having more number of tuples. Some other disk will be having more number of tuples available. So there will be differences in the completion time for any operation, for any execution. It will be differing. Now if there is no skew in the partitioning, if there is no skew means everywhere the partition is almost equalized. There is no overhead due to the parallel evaluation. So all the processes will be executing the task within a limited or given time. So there will not be any imbalance between the different processes, and there will not be any extra time taken for the completion of the entire task. So if this is the situation, that is, if there is no skew, the expected speed up will be always 1 by n. 1 by n is the total number of processors or total number of disks available. Now if there is some skew and if there is some overhead that is already available within these processes, mainly because of this skew, the time taken will be estimated in a different formula. You can see that is T part plus T ASM plus max of T0, T1 up to Tn minus 1. So what are this T part? T part is the time for partitioning the relation. So we are going to consider the total time taken for completing the parallel operation. So T part is the time for partitioning the relation. So for any parallel operation, initial thing that we are going to do is we will be partitioning the relation so that the tuples can be distributed among different processes. So initially it will be having some time for partitioning this relation. So this is called as T part. So that time will be wasted here. Now TASM is the time for assembling the results. So after getting the results locally on each of the partition, finally we need to assemble or gather all these results into a single processor. So that will also take some time. That is called as TASM. So first partition time. Now this is the assembling or gathering time, plus we will take the maths of T0, T1 up to Tn minus 1. So these are the times taken for the operation at each processor Pi. So maybe some processor, if it is having skew or overhead, it will be taking more time. Some other processor, if it is having less skew or less number of tuples available, it will be taking only less time. So here, in order to evaluate the total time that is taken for the completion of the entire operation, we will consider the maximum among all these times. So whichever processor is taking more time for completing the task, that will be considered here. So the partition time plus the assembling time plus the time taken for the larger task will be evaluated, or this will be the estimated cost of the execution of any parallel operation that are applied into a parallel system where the operations are being executed in parallel in intra-operation manner. So it is actually depending on the skew. So this maximum of time will be actually depending on the skew, that is the imbalance among the distribution of tuples into different sites or different processes. So that is all about intra-operation parallelism. So we have seen several example operations, several algorithms for sorting, some algorithms for join operation. Then we have seen parallel selection, parallel duplicate elimination, parallel projection, then parallel aggregation or grouping, and finally we have seen the evaluation of cost for the parallel execution of a single operation or intra operation, or when we are implementing an intra operation parallelism. Now in the next session, here we will be discussing about inter-operation parallelism. So this is not a very big topic, so we will be discussing with a very few examples here. Inter-operation parallelism, which is the direct opposite of intra-operation parallelism. So what is this inter-operator parallelism? In the previous example, join, the same join operation is being executed in parallel, or the same sort operation is being executed in parallel. But here, different operations, maybe the same operation also, but more than one operation they are executing in parallel. For example, two join are to be executed in parallel, two different joins. two different joins on different relations. So that is actually interoperation. So first join, second join, they are considered as two different operations. But previous case we will be trying to apply a single join, then distribute and execute that join parallelly. But here different operations are maybe of same type or maybe of different type, whatever be the type of operation, but multiple number of operations that are executed together in parallel, that is called as interoperator parallelism. So consider an example of a join operation on four relations R1, R2, R3 and R4. So look at here, we want to perform an operation R1 join R2, join R3, join R4. So this is a situation where we need to handle a huge operation that consists of four relations, and this is to be joined in this particular manner. Now one of the mechanism that can be used is a pipelined parallelism. So this interoperator parallelism can be done in two ways. So here in this slide we will be discussing about the first mechanism, that is called as pipelined parallelism. So if this is the input or this is the operation that is to be performed, we can set up a pipeline that computes the three joins in parallel. So we'll be remembering pipelining, how we are doing pipelining in our system design architecture subject. We were discussing in detail about pipeline. That means one stage of first operation, then the second stage, third stage, they are being interleaved by using different components, different processor parts. So like you'll be remembering about memory write, reading, then processing, CPU execution, etc., etc. We'll be having a different stages of operations that is to be executed in an interleaved manner. That is actually called as pipelining. So here how we can apply pipelining on these join on four relations R1, R2, R3 and R4. Now let P1, one processor P1, it will be assigned the operation R1 join R2. So temp1 is equal to R1 join R2, that be performed in processor P1. So here we are going to discuss about pipelined parallelism. Now the second processor P2 will be assigned the computation of temp1, that is a result of this two join R3 in the second processor. Now in the third processor, the result of temp2 will be joined with R4. So if these three processors are being utilized for this join on 4 relation, we can follow this pipelined fashion. That means R1 join R2 execute at P1, then the result of that join R3 in second processor, and the result of the second processor join R4 in the third processor. Okay, so the P1, the entire execution will be taking more time, but in the first stage initially it will be selecting, while joining it will be retrieving some tuples. So whatever tuples it is generating, that can be given to the second processor, and the second processor will be producing some tuples, and from here that can be given to the third processor. So the P2 is not waiting for the completion of entire P1. Similarly, P3 is not waiting for P2 to complete the entire operation on P2. Whatever tuples each processor is generating will be forwarded to the second processor, so that it can perform this join on those set of tuples that are already being generated, and that will be joined, and the intermediate result will be given to the next processor for the remaining join operation with the other relation. Now each of these operations can execute in parallel. Sending result tuples, it computes to the next operation even as it is computing further results. So each processor will be active at any time, but intermediate results are forwarded to the next processors to come. So it will be like the entire task will be completed in less time by implementing this pipelined parallelism mechanism. So this can be executed, this can be demonstrated in a pictorial way. Here you can see in the processor P1, R1 and R2 will be joined. R1 and R2 will be joined here, and the intermediate results are forwarded to P2, and P2 will perform the result of this join R3. Then intermediate results are forwarded to P3 from P2, and that will be joined with R4. This thing will be continued. Now in the form of processes, here R1 join R2 in this disk on P1, this will be performed and it will be passing the result to P2, and in P2 the results are maintained in the disk. The result will be joined with R3 here. Then the results are given to P3 from P2. Here the result will be stored in disk, and that will be joined with the relation R within the disk of P3. And finally, after the entire tuples that are being joined, the final result will be stored in a particular processor that will be normally in the final processor, that is P3. This is the parallelism, that is an example for inter-operator parallelism, which is using a pipelined fashion of doing parallelism. That means there is no independent execution. All the processes, some portion of the different operations will be executed, and one processor is depending on another processor for the completion of the entire operation. So this is an example for one inter-operation parallelism. Join itself, but multiple joins we are going to do in parallel. That is why it is called as inter-operator parallelism. Now the different factors that limits the pipelined parallelism is, the pipeline parallelism is useful since it avoids writing intermediate. So when we are using pipelined parallelism, we don't need to write the results, intermediate results into the disk. So directly the results will be joined with the second relation that is present in the second processor. So we don't need to write the results every time whenever we are getting the intermediate results. So results are directly passed to the second processor for the join with the next processor. Now it is useful with small number of processes. So the factors that limits pipeline parallelism is, as you know, pipeline parallelism cannot be employed in a very large situation like with a more number of processes. So it is useful with a situation where we are having a very few number of processes available. So that is one issue with pipeline parallelism. Now next point is, it cannot pipeline operators which do not produce output until all inputs have been accessed. That is like aggregate and sort. So in every operation we cannot apply this pipeline parallelism, where we need to get the result of an entire operation, and after getting the result move towards the second. In that situation, this pipeline fashion is not a good approach. Similarly, a little speedup is obtained for the frequent cases of skew in which one operator's execution cost is much higher than the others. So when we are using pipeline parallelism, we can have only very little speed up when we are having some skew variation and all. So normally the problem with this pipeline parallelism is it cannot be applied in a very large architecture. I mean, it is always helpful for a situation where we are having only some 2 or 3 processes available for the execution. Other situations we need to go for a second inter-operator parallelism mechanism that we will be discussing in the next slide. So the second mechanism that is called as, the second method of applying inter-operator parallelism is independent parallelism. Independent parallelism means different operations or independent operations are executed independently on different processor. So in the previous case, all these operations are depending. The second processor is depending on P1, third processor is depending on P2. So there is a dependency there in the pipelined parallelism. But in the case of independent parallelism, we are not having any dependency on other processes. So consider the same join operation here also, R1 join R2 join R3 join R4. Now what we are going to do is, in the processor P1 we will be assigning R1 join R2, first portion. Then into P2 we will be assigning R3 join R4. So this is one session and this is one session. They are independent. And in the P3 third processor, we will do temp1 join temp2. The result of R1 join R2 is stored in temp1, and R3 join R4 is joined in, that is stored in temp2, and this result will be temp1 join temp2 will be evaluated on processor P3. Now we can see that P1 and P2, they can work independently in parallel without depending on any other processor. So P1 is entirely independent and P2 is also entirely independent. Now the problem with P3 is P3 need to wait until the completion of P1 and P2. So it will be wasting some time for P3. So what we can do for that is, we can pipeline the output of P1 and P2 to P3. So intermediate results can be directly pipelined to P3. If this is being followed, gradually P3 can also start calculating temp1 join temp2. Now previous case what I was mentioning, R1 join R2 entire operations to be completed, then R3 join R4 entire operation to be completed, then P3 will be evaluating temp1 join temp2. But if you apply some pipelining here, that is R1 join R2 is independent, R3 join R4 is independent, but R1 join R2 will be producing some tuples and move that to P3. Similarly, R3 join R4 will be producing some tuples, move that to P3. Then it will perform gradual, that is some tuples of temp1 will be joined with some tuples of temp2. Similarly, whatever tuples it is generating from both P1 and P2, one by one they can do joining, and finally we can save little more time by increasing the speed of P3 also. So independent execution of P1 P2, then P3 waiting and finally calculating this join will take more time, and it is always better to apply pipelining on P1 and P2 to P3 for combining the independent parallelism and pipeline parallelism. So the problem with this is that it does not provide a high degree of parallelism because most of the time most of the operations are depending on one another, and also we always requires more number of processes for having the execution of more number of operations in parallel. So practically it is a very costlier, as well as it is difficult to implement a high degree of parallelism because always we will not be having independent operations. So we cannot always say that it will be having a high degree of parallelism. It is also useful for a low degree of parallelism situation. So this was the operation that was given in this example. So R1 join R2 will be produced at P1, then R3 join R4 will be produced at P2, then P1 join P2, or it will be executed at P3, and P3 will be producing the result of the entire join operation. So this is the second way of implementing inter-operation or inter-operator parallelism by using independent parallelism mechanism. So like the sorting algorithms and the join algorithms which are important for the intra-operation parallelism. Similarly, for inter-operation parallelism, this pipelined parallelism and independent parallelism, these two algorithms or these two mechanisms are also very important. So here we were discussing about the different approaches for increasing the speed up or speed of execution using parallel databases. So we were focusing on parallel databases so far, various mechanisms for implementing parallelism on the database operations. Main separations were inter-query parallelism and intra-query parallelism, and there we are having distributions like intra-operation parallelism and inter-operation parallelism, and we are highly focusing on these two parallelism, inter-operation and intra-operation parallelism, and various algorithms related to these concepts on various example database operations. So that is all about parallel databases. In the previous three videos we were mainly focusing on parallel databases and various approaches for implementing parallelism on the parallel database systems. Now in the next session, in the upcoming videos, we will be discussing about distributed databases and its features. Thank you.